Hello and welcome back, everyone. My name is Troy Bargman, and I'm excited to bring you another episode of TechXperts. This is a series meant to showcase innovative technology in the industry that brings meaningful change to our communities. Today, we have Ben Lindner from Alynix on with us. He's going to talk a little bit about drones, UAV, but more specifically, bridge inspections and their Decker program. Thanks for coming on, Ben. I appreciate it. Could you tell me a little bit about yourself and what you do for Alynix?
Yeah, I'm Ben Lindner. I'm the president at Alynix. We're a geospatial technology company, one of GBA's newest affiliates, and we kind of handle all things that is making maps and models with remote sensed information.
Awesome. You guys partner with a company called BAM Tech, right?
So BAM Tech is our direct-to-customer brand.
Okay.
So BAM Tech is where we offer the latest and greatest spatial solutions, and where spatial solutions puts together hardware and different software workflows and helps people get to deliverables with all this new technology that's out there.
Okay, nice. Could you tell me, you guys use UAV and drones, right? There is a difference between the two?
So I think it's just a difference in nomenclature, maybe.
Okay.
So UAV stands for unmanned aerial vehicles.
Gotcha.
Really, we look at all different sorts of platforms to collect remote sensing data. So sometimes we say from seafloor to satellite. So maybe it's a autonomous boat, or it could be a boat with people in it that has different sensors on it that are collecting things underwater. We have trucks and vans that we can put equipment on to collect information in a very efficient way. Sometimes it does end up being on a drone or an unmanned aircraft system. And sometimes we even work with helicopters and airplanes.
Oh, wow. So you're not just limited, I guess, to remote technology per se.
We're not just limited to autonomous technology at this point. Really, it's about finding the right fit of technology, the right fit of platform for what the customer's need is. So there's a lot of really cool and interesting things we can do with drones as far as resolution and being able to do things in a very fast, efficient manner, but there's also limitations to what drones can provide. So really it's about pairing the right sensor with the right platform so that you can get the data collected the most efficiently.
Okay. And then you say sensor, could that be just a sensor? Is that a camera? Is that a microphone even?
So sometimes sensors are microphones. So for instance, when we're doing like an autonomous boat solution, that would have a type of like sonar on it. So where we send out a sound wave and it reflects off something and we listen for that reflection. Sometimes sensors are as simple as like the camera in your pocket on your cell phone. Okay. We've got different platforms that fly very similar cameras to that, or sometimes we collect information with cell phones. Other popular technology we use is LiDAR.
Yeah.
So actually sending out pulses of light and then collecting those pulses of light back. So a lot of iPhones have LiDAR built into them, but then we also have very complex LiDARs that can range into the $500,000 to $1 million range that fly on the bottom of helicopters. We have a really exciting LiDAR right now on a drone that we just got to help launch called the L2. It's part of DJI's series and brings really what traditionally was like $500,000 technology into like a $15,000 price point.
That's nice.
So really interesting stuff happening there.
Yeah, that's really cool. So we talked a little bit about sensors. What drives a sensor choice, or why would you choose a certain type of sensor?
There's probably a few different ways we evaluate what type of sensor we're going to choose. It typically comes down to like what's the question you're trying to answer and what's the most effective or efficient way to answer that question. We can make really cool 3D models of the world by taking a bunch of pictures from different angles. That's a process, that's a science known as photogrammetry.
Okay.
And so if we know something about the geometry of the lens that's used to take a photograph and how it's striking a sensor, and we know something about where that sensor was located in the world, we can use that information to look at multiple photographs of the same thing from slightly different angles, and we can find commonalities and we can build a model. But that requires a lot of computational power on the back end to actually build that model. Versus if we were to use something like LiDAR, like on your cell phone, for instance, we can actually take direct laser measurements, and a lot of times that data can be processed in real time, and maybe we can get the same information. And so that's where efficiencies need to be looked at, and there's a couple efficiencies. So there's the computer processing efficiency, but then there's also cost efficiencies. And so like a cell phone camera or a 20 megapixel digital camera is a lot less expensive than a sophisticated calibrated laser measurement device. And so sometimes you select based on the cost efficiencies. And then we have other issues that we like to consider, which is what we can see is what we can get. And so when you use a traditional camera to do like a photogrammetry model, you can't see through vegetation because all you see is the grass, right? All you see is the bushes on a site. All you see is things like that. And so you can end up with a really great model of the vegetation. And sometimes if the client's like an architect, that's great. It's something that they can put their rendering into, and we can get a really good 3D model and really good situational awareness. LiDAR has some interesting phenomena, and that is, if you think about a LiDAR like a flashlight, so when you shine a flashlight at the wall, the further away from the wall, the bigger that beam gets. Sure. So LiDAR, even though it's a very concentrated point of light, there is some divergence or some spreading of that beam that happens when it contacts something. And so we can use that to our advantage. And so as it's passing through, for instance, a tree like the plant behind you, parts of that beam are going to hit the top of the tree, parts of that beam are going to hit some of the branches in the middle, and parts of that beam are going to hit the ground underneath. Okay. And so we can look at those different reflectance or the different ways that those come back to the sensor, and we can actually model not only the tree, but also the ground that's underneath the tree. Okay. Same thing with, we might choose an infrared sensor to look at something versus a regular camera. By measuring the temperature of something, sometimes you can see things inside it that you couldn't see if you were just looking at the visual spectrum or the visual light that it reflects off something. Okay. And vice versa, sometimes with an infrared camera, you can't see all the detail that you can see on the surface of an item like you could with a visual sensor. Yeah, okay.
So you could do the same project with 10 different sensors, really, but then it's more or less how much detail the client wants and asks for and the cost or the budget that they have.
Potentially, yeah. And then honestly, we do that quite a bit. So one of our really exciting systems is called the Specopod. And what's neat about the Specopod is its ability to fly multiple sensors at the same time. So it's a pod that's been developed that can get strapped to lightweight aircraft, whether that be a fixed wing aircraft or whether that be a helicopter, without the need for any extra FAA approval. So it's got a type of mounting system that's already approved by the FAA. And then within this pod, we have what's kind of like what we call a cheese board. And what it is it's just a bunch of screw holes. Okay. And those screw holes we can put different sensors into. So typically we'll fly like a LiDAR, and we'll fly 2 high resolution visual cameras, and we'll also typically fly an infrared camera. And what that configuration is used for a lot is utility line inspection, so like transmission lines. Yeah. And in order to make a model out of all that information, you have to do what's called a kinematic correction. Okay. So kinematic's just a fancy word for like movement, things that are moving. So if I take a laser tape measure and I want to figure out, how far away this microphone is from me, that's a pretty easy measurement. But if I want to take millions of measurements of this microphone in real time, and then turn those into a 3D model while the laser's moving through space, that's a harder measurement. And then if I want to pair that camera data up to it, I also need to do a more sophisticated measurement. So kinematics is basically how do we bring the sensor data into like a common known space where we understood where the sensor was and how the sensor was moving to make the model. Yeah. A couple different technologies we deploy to do that. So one is an inertial measurement unit. So it's called an IMU. And that's kind of the thing in your cell phone. If you've ever flipped your cell phone outside and the screen changes direction, it's because your cell phone has a really inexpensive IMU in it. Okay. If you've ever played a racing game on your cell phone and you're able to steer with your cell phone, it's all being done with the IMU. Okay. We also use GPS signals. So you can use 2 different GPS signals and you can tell how a device is moving, or even a single point GPS signal will tell you how a particular sensor is moving through space. So those are probably the two main things we use to do kinematic corrections. But what's cool about this cheese plate is traditionally we'd have to come up, if we put a laser and a couple cameras together, we'd come up with a very specific kinematic correction for that laser and those couple sensors. Okay. Having this cheese plate to attach these things on, we can have a really good idea of approximate position of those sensors. Yeah. And so that allows the people operating the systems to change these configurations in real time. Okay. So sometimes the utility will want you to look at transmission lines from the side, or they'll want a very specific view angle on it because they know they have a very specific type of connector or something on there that they need to examine. And then you might go to the next utility and they might have a different requirement. Well, instead of buying all new sensors and building one package that's very specialized, we can change these things out in real time.
Gotcha. And then you adjust your parameters on your correction.
Yep, you let our software know, where is the laser this time, where's the camera this time, what is the angle of the laser, what is the angle of the camera, and then it can specify the new kinematic correction so that when you post-process all that information, you can put it together as a single piece of a single model.
Right.
So
just, different layers.
When you do a LiDAR measurement, that one of the ways this is most typically used is when you do a LiDAR measurement, that data actually comes back and it's basically black and white, or it's in actually an intensity format. It's the intensity of the reflection. Okay. And that can be very useful to some sort of computer algorithms that are looking for certain things, such as geometry or structure. But it can be kind of confusing to a human being that's trying to figure out, is that grass, or is that dirt, or is that a street sign, or is that a car? So being able to apply the individual pixels from the visual cameras to that point cloud, we can colorize the point cloud. Yeah. And then you end up with a point cloud of all those individual laser measurements that looks more realistic or looks more lifelike, giving you a lot of situational awareness.
Gotcha. I remember Terry was talking about kind of look like pointillism if you colorized your intensity scale, I think. Yeah. So intensities is something we use a lot in transportation with LiDAR. Yeah. So actually looking at the intensity of the reflection, we can tell something about what it reflected off of. Yeah. And so, for instance, if you want to look at pavement marking or striping, actually sometimes looking at the intensities is better than looking at the color corrected point cloud or the colorized point cloud, because we all know that paint lines fade. Right? Yeah. Well, actually looking at the intensity, you can get these very crisp edges of where the paint lines are and where they're supposed to be. Okay. Same thing when reading road signs. Sometimes using an intensity reading is better than actually looking at the colorized point cloud. Seems counterintuitive.
Yeah. Well, it's about how machines look at things versus how humans look at things, right?
Yeah. So that's why.
Being able to have a algorithm go through a point cloud and try and read what a sign is. Maybe the difference between black and yellow on a road sign doesn't mean as much to the computer as if it can look at that intensity and actually see a sharper line. Okay. And then part of that too is just the process of kinematics of applying the visual spectrum to the point cloud. Those algorithms aren't perfect, so sometimes you'll end up with fuzzy lines versus that intensity line's almost very sharp because it's only coming from the one sensor. Right.
Okay. Well, so, talking about transmission lines or LiDAR and roads and stuff, how would you go about deciding sensor and vehicle and everything to actually get to that solution?
I think it always comes down to decision support. So you got to start with what is the decision your client's trying to make. So maybe the decision your client is a civil engineer that's looking at a suburban street infrastructure, and they want to figure out the best ways to improve that infrastructure. And so they'll have one set of decisions that they're trying to make as far as, they need very precise measurements of the slope of the ground so they make sure that the drainage is right. Sure. Or maybe they need very detailed information about, the existing paint lines or the existing signs. You might have another client that's trying to do like a countywide inventory of all their signs that they have, so they understand what they need to maintain. Well, maybe those measurements don't need to be as precise, but you have to be able to capture a lot of data in a lot of ways. Yeah, that's how we'd start to spec that out. Same thing if I look at, we do a lot of like interior modeling for like bridge, for like building projects, or either as-builting or retrofitting an existing site. Sometimes it's really important to have really exact measurements because you got to make sure that a tank can get through, an opening, and you want to build that tank as big as you can possibly build it and make sure it can get through. But other times, maybe we just need situational awareness to understand where all the existing piping and things are, and you're not as concerned about where it is in space. And so sometimes the difference between those decisions could be the difference between using, a sensor that costs tens of thousands and a sensor that costs hundreds of thousands of dollars.
Okay.
It might also be sometimes we're really concerned because we want to take part of the design that we're going to do, and we want to give that design to like a machine that's going to grade the land or move dirt around. So in that case, it's really important that we understand where that model is in space. Other times, if a mechanical engineer is just looking at like where to put the next, HVAC duct, they may not care at all where it is in space. They just want to know where it is relative to the rest of the building. So that would again change the different technology that we'd approach that problem with.
Okay. So you can do a lot of cool stuff then with drones and remote technologies and really just about anything, it sounds like. So can you tell me about Decker and what that program is?
Yeah, so Decker's a product that we're bringing to market, just launched it this year, and it's really based around trying to get as much autonomy as possible to create efficiencies with some of the things that have been happening prior in remote sensing. So there's this phenomenon called bridge deck delamination, and basically that's when parts of a concrete structure start delaminating from the rest of the structure. It is a phenomenon that you want to be able to inspect and get insights about. There's been a lot of different approaches to this over the years. So the most traditional approach, I think, is what we call sounding, and that's basically taking some sort of metal and hitting concrete with it, and then using your human ear to hear if there's anything that sounds shallow or hollow, like it would be dividing from the rest of the structure. And a lot of people have tried to use other sensing techniques to improve upon that over the years. So one popular way is what they call acoustic sounding.
Okay.
So it's a fancy way of doing the human version of slapping chains onto a bridge and listening to the sound. So what that is like a cart that you'd roll across a concrete bridge deck, and the metal rod would slam into the concrete, and then you'd use microphones to hear the difference, and you'd map that way. Ground penetrating radar is another way, where we'd use radar signals, which is basically a radio frequency that we would project into the concrete and then listen for the reflections. And then a lot of people have been using infrared, and primarily the way infrared would be deployed would be either on a helicopter or an airplane, which provides a signal, but maybe a lower resolution signal, or sometimes they put infrared cameras either handheld or in vehicles to look for this phenomenon. Which all have their different advantages and drawbacks. So with an aircraft, maybe you could look at a lot of bridges at once, but your resolution would be lower. With a system that's attached to a vehicle, maybe you could look at less infrastructure at the same time, but you get a higher resolution signal. So basically all these different types of inspection that we've been doing on bridges, all of their advantages and disadvantages, and we've tried to build a product that gets rid of as many of the disadvantages as possible. So we realized early on when we were developing technology on drones that this is an area that needed some improvement as far as using the infrared camera on drones to find delamination. So we got a couple issues there. Primary one being that the infrared cameras that come on drones right now are not the most sophisticated camera. So a lot of them were developed to help find, like kids in cornfields, is what we say. So they were built for, emergency response and things like that. Maybe to help like police pursue a suspect or things like that. And so we figured out that we needed to improve the data quality that was coming out of these sensors, but that these inexpensive sensors could lead to a lot more proliferation of this technology. So really turning this into a product, we've done a lot of work to make it as autonomous as possible. So we now have a platform that flies itself, has a box that manages the drone itself, recharges the drone, manages what's happening with the weather, takes off and lands, also manages the data, so it downloads the data automatically from the drone and sends it via satellite, a Starlink actually, to our servers that do the processing. And then the other problem we saw is even if you can get good quality data out of these sensors, the traditional approach to detecting these anomalies in the bridge deck would be to have somebody called a thermographer look at all the images. It's a lot of images to look at, and if you gave this two thermographers the same data, sometimes you'd end up with different answers. So we spent a lot of time automating that process so that we get a very consistent answer coming out of the software platform.
Okay. That was a lot.
Yeah.
But I guess, so traditionally speaking, I mean, you would have to shut down lanes of traffic and have somebody out there listening for an audible difference. So now you're using a drone, right? And as you're working out all the autonomy, you have somebody physically flying that drone then, I assume?
So we don't anymore. Okay. So now the drone flies itself.
Right.
We still have to supervise the system depending what sort of waivers we have from the FAA for that particular project, but the drone is completely autonomous. So the drone in a box, it's actually a trailer. So a trailer manages its own power, its own communications.
Oh, wow.
And then there's actually a box that manages the flying of the drone. And all this is run off a software that we have that runs in the cloud. It runs on a server in Cleveland, Ohio. And we can manage it from the office and also in the field with our technicians, keeping an eye on everything.
Okay. You're not having to shut down traffic, are you?
No. So all the other approaches for the most part require some amount of traffic control. Yeah. So if you're a person out there hitting a piece of metal into the concrete, you definitely need to make sure there's no traffic flow, so that interrupts traffic. And even some of the other methodologies either have to significantly slow down or stop traffic to make them work. Our technology operates about 125 feet above the bridge deck, and we're able to do it while there's live flow traffic. So part of that is in the magic of how we collect the data. For every given waypoint in time, we collect almost continuous imaging, usually about 15 shots per spot, and that allows the live traffic to flow underneath, and then we can compile all those into a single image that are absent traffic.
Okay, that's really cool. That's pretty awesome. So then I guess specifically, once you have all that image, it would be a temperature difference that you're seeing?
Yeah.
Okay. Is it hotter or colder?
It could be both.
It could be.
So we actually collect data from sunrise to sunset.
Okay.
We think that that is the way that we can get the best answer possible about what's happening with the bridge. And so to think about it, kind of the easy way is small rocks and big rocks.
Yeah.
So if you had a large rock in a field and you had a small rock in a field,
sure,
the small rock's going to heat up and cool down faster than the big rock.
Yeah.
And so when we're looking at delamination, the parts of the structure that are becoming debonded from the rest of the structure, they'll heat up or they'll cool down faster than the rest of the structure. So typically when we take our first images in the morning, the parts that are debonding show up a little bit cooler because they've had all night to cool down.
Okay.
And there's typically air and stuff flowing across the bridge deck that's pulling heat out of the structure, and so that makes that cooler. And as the sun starts to heat the structure up, we'll start to see that those parts of the bridge heat up faster than the surrounding bridge. And then at some point, it all kind of equalizes throughout the course of the day, and that gives us a good idea of what's delamination and what could be another phenomenon that's on the bridge deck. So somebody spilled paint on a bridge deck, or everybody's driven over a bridge deck and seen tar balls. Those sorts of things can also heat at a different rate than the concrete, so we need to see the difference between those and the actual concrete debonding.
Okay.
And that's why we look for the equalization. And then going into the evening, as everything starts to cool down, we'll start to see those delaminations cool down faster than the surrounding.
Gotcha. So it's more or less the rate of temperature change that you're looking for.
Yeah.
Okay.
It's a really good way to think about it, and define that within all the background signal too is something that's a big concern to us. And You think about it, as we fly the drone and we collect these 15 images at a particular time and space, we combine those all into an image. And then as we do that throughout the course of the day, that's the time series, we have to get each one of those pixels to be as spatially accurate as possible to the next pixel we want to compare it to.
Okay. So that's fixed location or fixed imagery, or where you're taking the picture. Basically.
Yeah, so we can never get the drone back to the exact point in space.
Yeah.
The drone technology's gotten really good to where we can get it within about a golf ball of where the picture is taken. But there's a lot of things affecting the drone. So it could be a gust of wind, or it could be just, a difference in how the autopilot reacted at a particular point. And so there's always a little bit of wobble. So getting all those images perfectly aligned is a lot of the secret sauce that makes the process work.
Sure. Okay. Are you using AI to help with any of this?
AI. So when we think about AI, I think that there's a lot of different types of things that are labeled as AI in the marketplace. So there's a lot of models that use language and try and act like a person, or there's models like Siri on your phone, right? It tries to listen for sound waves and puts those patterns of sound waves and it tries to guess what words you're saying. So those are forms of AI. The type of AI, I guess you'd say, that we work primarily in is really in the field of computer vision.
Okay.
So it's about computers being able to recognize imagery and do different things with it. So doing all that alignment is a computer vision problem. There's also we need to segment our images. So we need to be able to tell the computer what's bridge deck and what's guardrail, or what's bridge deck and what's grass next to the bridge.
Okay.
And so image segmentation, we definitely use some models there that use machine learning to recognize previous inputs. So that'd be maybe a type of AI. But yeah, overall, it's computer vision is probably the main technique that we use, and then we do a little bit of teaching to computers, which I think is associated with AI, and whether that's a type of neural network or ML is what it's primarily called, different machine learning models, and then we test the outputs of the information that we've used to teach that model, and it definitely helps get through the data faster.
Yeah,
but a lot of it's just running math in ways that a human being never could. It's another way to think about it.
Yeah.
So, you think about your typical algorithm equation, right? There's only so many times we could do that on a piece of paper in front of ourselves, right? So a lot of what I think is labeled AI is sometimes just us doing math in a way that humans can't do. And so I don't know if it's necessarily intelligent, but it can lead to intelligent insights.
Gotcha. Okay. That makes sense. So not necessarily a true artificial intelligence, but definitely using computers to help drive those calcs.
That being said, I think there's a lot of opportunity with our product to be a little bit more AI driven in the future.
Yeah.
So everybody this year has heard about ChatGPT. Everybody's read an article, and maybe you've played with it, or you've downloaded something on your cell phone that helps make you sound smarter, write better answers, right? The reason that ChatGPT works, it's called a transformer model. And what it is it's a model that's been built on a lot of data. And so the data that we had to build the transformer model that powers ChatGPT is language. And so we have a ton of digitized language. Almost every book ever written has been digitized in some format. We have all this search engine data from people looking for different things. We have blogs, articles. On the sound side of things, turning sound waves into language, we have all the different recordings. This recording could be used to train an AI model, right? And so the reason these transformer models work so well is because we had all this digitized data to train it on how to work. One of the struggles we have when we're doing remote sensing or we're looking at solving civil engineering problems is we don't have a lot of digitized infrastructure.
Sure.
And so that's one of the opportunities with this product is if we find a way to affordably offer a solution that can give us a better answer than we have today, in the same time digitizing that infrastructure. And so, 5 to 10 years from now, hopefully we have millions of bridge decks that are digitized.
Yeah.
And then we can take that data and we can take weather data and we can take construction data and we can start to train models that might be able to help us predict or do insights that would probably feel a little bit more intelligent than what the systems are doing right now. And so
Gotcha.
Decker definitely can't guess where bridge delamination is occurring. That's not really what it's trying to do. It's trying to detect a signal and tell us where bridge deck delamination is occurring. But if we get enough of those digitized maps, in the future, we could maybe have a program that would say, you need to go look at bridges that have this type of construction characteristic and maybe have experienced these weather conditions, or maybe have had these types of chemical treatments, or maybe had this type of deck overlayment done on them.
Right.
And so that's really where the power of something that probably looks more like AI could show up in infrastructure inspection.
Okay, that makes sense. So nothing right now, but something that could be.
I wouldn't say nothing right now. It just kind of depends. A lot of stuff is called AI right now.
Yeah.
And the question I always ask myself when I'm reading a piece of marketing or I'm reading about a product or looking at something that calls itself AI is, what is it doing that's intelligent?
Yeah.
And so you could say, like, being able to look at tens of thousands of images and getting them aligned very perfectly, there's some intelligence happening there.
Sure.
And it's definitely artificial. It's definitely happening by a computer. I think a lot of stuff that gets labeled as AI, though, is currently just doing stuff that humans couldn't do.
Okay. That makes sense. What are some of the next advancements that you see for Decker? I mean, it sounds like maybe more sensitive sensors or better quality sensors.
I think sensor quality will continue to improve.
Yeah.
I think the biggest advancement that we'd see in Decker is if we start to get a lot of data and what we think we could do with that data in the future. Right now, it's about proving a commercially viable model. So we've been performing these services with a drone and an infrared camera, and human operators and human thermographers doing the service. And in the past, we were able to offer these the solution for anywhere from $20,000 to $50,000 a bridge, and so that really limited the types of bridges we could look at. We typically only looked at bridges that were about to go under construction.
Okay.
Well, the goal with this solution is to be able to do the same thing in a more repeatable way for hundreds of dollars a bridge. And so the deployment of our system right now is really going to prove out if the market can bear that hundreds of dollars a structure, and by bearing that, are we going to be able to collect enough data to continuously improve on the product? So I think sensors and drones will always get better, computing will always get better, and that'll all drive down the cost. And the more we drive down the cost, the more we can use these solutions in a system-wide approach. So let's look at all the bridges that we possibly can versus just looking at the bridges that have problems.
Sure.
So I like to compare it a lot to like healthcare.
Okay.
So a lot of people wait to go to the doctor until they feel like they're having a heart attack. And then when you go to the doctor, you've got to get EKGs and you got to maybe get an MRI or some sort of scan on your body. And you got to get really detailed information so that they can figure out how to fix you. I really want Decker to be more of a blood pressure cuff. So I want people to regularly check their blood pressure, and then when their blood pressure starts to rise, they know to go look at that bridge. And so if we can make Decker act more like an Apple Watch or like a blood pressure cuff, to where you're continuously checking the health of your infrastructure, I think that's a really big opportunity.
Yeah, that would be super exciting. Predictive maintenance on infrastructure. That'd be awesome.
Not predictive, but just regular diagnostic, regular checkups. So we know that we can chain drag a bridge when we have to figure out how much quantity of concrete we need to fix it. But the federal requirement is that we're looking at our bridges every 2 years. Well, depending on where the bridge is and how much traffic it has, sometimes we don't get to always do a detailed assessment of the deck. So come into a solution that's affordable enough that it can be worked into that, every 2 year checkup. We have to go to the doctor every year to get our paperwork filled out so we keep our insurance costs low, Same sort of thing. It'd be really nice to actually be getting a full picture of what the deck condition is every couple of years during the routine inspection process.
Okay.
Yeah, it's definitely an exciting field we find ourselves in. I think the possibilities that open up literally every day. Every day we'll have a client come to us with a different problem, and it's really fun to look at how do we take kind of our toolkit of different different solutions and figure out the best way to combine those to solve a problem or to help somebody make a decision. The consumer electronics revolution has really brought the price of a lot of this equipment into a lot of new applications that it was never possible before. The proliferation of computing, our team can literally with the click of a button spin up petabytes of processing power on a server within minutes, and that really leads to the potential of a lot of interesting things happening there. Also, a lot of companies and firms taking advantage of services like that have really driven down the cost. And so, we can run things for thousands of dollars today that even 10 years ago would have been hundreds or millions of dollars to try and compute in the past. So all that stuff is really leading to this cool revolution where really there is unlimited possibility now. There's just so many different things we can do. That being said, it's important to know the limits of technology,
right,
and to really understand. That's part of the decision-making process, is being able to help your client understand how well they can trust the model that we built, how well they can trust the situational awareness that we have. And that's a big part of being successful with these technologies too, is to scope it correctly. You could make a model of a factory floor, and you could model all the way down to like every individual thread on a bolt, right?
Yeah.
But who's that serving? Like, how does that help? And so that you could do that theoretically, but it's probably more costly than the model you need, which is you might probably just need to know there's a bolt there.
Yeah.
And you need to understand the spacing of that bolt. You need to understand the spacing of that bolt pretty accurately if you want to pull that piece of machinery out, put a new piece of machinery in. But you probably don't need to know where every thread is. Right? And, so we spend a lot of time conceptualizing that with clients as far as understanding, like, what do you really need to know, and then that helps us figure out what we need to model and how accurate those models need to be, and then also making sure that they understand how accurate the models are.
Okay.
You can never, it's almost impossible to measure something twice and get the exact same measurement. If you've ever done a home improvement project, like you've felt that when you cut a board too long or too short, and so there's this aspect of repeatability in measurements, and that is something that you gotta consider. And if you're validating a measurement, whatever you're validating that measurement with has to be a more accurate way of measuring than what you're trying to validate.
Right.
And so there does become a diminishing return of value there as you try and validate further and further. So what NASA would do to make sure that a satellite goes together is probably overkill on what we need to make sure that a new conduit system would fit into a warehouse. Right.
Okay. What type of clientele do you work with?
So we work a pretty broad sector. I think our major component of our clientele is civil engineering firms. A lot very similar to GBA, some that are more specialized in the geospatial part of the equation. We work with a lot of different types of government, so a lot of DOTs, but also we work with environmental parts of government, people that are doing modeling of the environment for different reasons. We work with a lot of utilities, so electric utilities, water utilities, directly with them sometimes. But typically it all kind of has a engineering flavor. It's somebody trying to help improve the built world or somebody trying to protect the unbuilt world.
Okay. I don't know that I have anything else. You got anything else?
I do.
No? Cool. Well, thanks for coming on.
Thanks for having me, Troy.
Appreciate your time.
Yeah.
Thanks everybody for, I guess, watching and listening in this for this episode. We'll catch you on the next one.